In the world of AI, what you see isn't always what you get. Today, we're diving into a really hidden flaw, something so wild it can make even the smartest AI systems basically hallucinate, seeing things that are just not there.
So here is the big question. How do you turn a panda into a gibbon with a change so tiny the human eye literally can't see it? I know, it sounds like a magic trick, right? But this is no illusion. It's a very real vulnerability, and it's hiding in a lot of the AI models we use every single day. So how on earth is this possible? Let's get into it.
Okay, so first we start with a totally normal image, a panda. We show it to a state-of-the-art AI, and yep, it correctly says that's a panda, with about 58% confidence. So far, so good, right? Nothing weird happening here.
But now, this is where the magic, or maybe the trickery, comes in. We're going to add something to this image. It's a very specific, mathematically crafted bit of noise. Now, this is not just random static, okay? You can think of this noise pattern as a secret key, one that's been designed specifically to unlock the AI's own blind spots. It's engineered to push the AI's understanding in the exact direction that's going to cause the most possible confusion.
And here's the result. To you and me, this picture looks exactly the same. I mean, identical. The change is totally invisible. But to the AI, it's now 99.3% sure that this panda is a gibbon. Wow, it's not just wrong, it is absolutely certain that it's right. This, my friends, is what we call an adversarial example, and it shines a massive spotlight on a huge blind spot in these algorithms.
Okay, so what in the world is going on here? For the longest time, everyone in the field just assumed these kinds of mistakes happen because deep learning models are just so incredibly complex and, well, weirdly nonlinear. But the paper we're digging into today, it points to something much, much simpler. And honestly, it's way more surprising.
Yeah, you heard that right. The main reason for this crazy behavior isn't complexity at all. It's actually the model's simplicity. The paper's big claim is that the real culprit is how these models behave in a surprisingly linear way when they're dealing with lots and lots of dimensions.
So here's the big idea, the linearity hypothesis. For an AI, a picture isn't a picture. It's just a giant list of numbers for every single pixel, right? So it's like a point in a space with millions of dimensions. And in that massive space, these neural networks act in a very straightforward linear way. What that means is, if you make millions of tiny little changes to the pixels, changes you'd never notice, all those little nudges just add up. And when millions of tiny nudges add up, you get one giant shove that just completely throws off the AI's final answer.
Think about it like this. Imagine you're on a super long walkway that has a tiny, almost unnoticeable incline. Like every step you take only raises you by a millimeter. You'd never feel it. But if you take 1,000,000 of those steps, you could end up at a completely different altitude on top of a mountain without ever feeling like you were climbing. That's exactly what's happening inside the AI's brain.
So knowing about this linear weakness isn't just about explaining the problem. Oh no, it actually gives us a recipe for weaponizing it. The researchers came up with a simple, incredibly fast, and just shockingly effective way to create these things on purpose.
It's called the fast gradient sign method, FGSM for short, and trust me, the key word there is fast. Before this, finding these weak spots took a ton of computing power. But FGSM is super efficient. All it really does is ask the model one simple question. Hey model, what's the one direction I can push this input that will confuse you the most? And then, it just gives the image a tiny, invisible nudge right in that direction.
So how does it work? It's basically a 4-step process. Step 1, you feed the model a clean image. Step 2, you calculate something called the gradient. That's just a fancy math term for finding the exact direction that will cause the most error. Step 3, you take that direction and create a simple noise pattern from it. And step 4, you add a teeny tiny amount of that noise back to the original image. And boom, just like that, you've created an adversarial example.
So just how good is this attack? Well, when they tested it on a pretty standard model that recognizes handwritten digits, it caused an error rate of 89.4%. I mean, just staggering. But believe it or not, that's not even the scariest part. It's this. The model wasn't just confused or unsure. No. On all those times it got the answer wrong, its average confidence was 97.6%. It was utterly, completely, 97% certain it was right, even when it was dead wrong. And that's the real danger here. These attacks don't make the AI uncertain. They create a false, rock-solid certainty. Okay, so the models are fragile. They're brittle. Can we fix this? Well, the researchers had a pretty clever idea.
It's basically fighting fire with fire. If these examples are fooling the model, why not just train the model on them?
And that's the whole idea behind adversarial training. You're basically playing a game against your own AI. You're constantly creating these tricky examples designed to fool it, and then you show them to the model and say, nope, this is still a panda, or hey, this is still the number 7. You're forcing it to learn to see past all that tricky, misleading noise.
And you know what? It works. The results are just dramatic. Look at this. The standard model, it gets bamboozled almost 90% of the time. But the model that went through adversarial training, its error rate plummets all the way down to just 17.9%. It actually learned how to resist the attack.
But here's something they probably didn't expect. This training didn't just make the model tougher against attacks. It actually made it better at its regular job too. By forcing it to learn what not to pay attention to, it got better at focusing on the important stuff. It even got more accurate on perfectly clean images. It's like a super powerful regularizer.
And you can literally see the change inside the model. On the left, you've got the features a standard model learns. They're kind of messy, a bit all over the place, but on the right, after adversarial training, look at that. The features are way cleaner, more focused. They actually make more sense to us humans. The model has truly learned how to zero in on what matters.
Okay, so let's take a step back and look at the big picture here. What does all this mean for the future of AI? Well, it points to a really fundamental trade-off, a tension right at the heart of modern machine learning.
And here it is. The very thing that makes these models so great, their linearity, which makes them easy and efficient to train, is also their greatest weakness. That computational simplicity is the exact same thing that makes them so vulnerable. This table really lays it all out. On one hand, you have linear-ish models like the deep nets we've been talking about. They're easy to train, but they're brittle, and they fail with this terrifyingly high confidence. On the other hand, you have different kinds of models, like these RBF networks. They're way harder to train, but they're much more robust. And here's the key part. When they do get confused by something weird, they tend to say, I don't know, by giving a low confidence score. And that's a much, much safer way to be wrong.
The authors of the paper put it perfectly. They said, ease of optimization has come at the cost of models that are easily misled. In our rush to make things easy for our computers, we've accidentally made things easy for our adversaries too.
And that really leaves us with a huge question for the future of AI. As we build ever more powerful systems, how do we design them to be not just accurate, but actually trustworthy? It's not enough for an AI to be right most of the time, especially if we're going to put it in a self-driving car or use it to diagnose diseases. It has to be robust, it has to be safe, and this whole panda becoming a gibbon thing is a pretty stark reminder that we still have a long way to go.